First off, I'll say I appreciate everyone who thought that on the last day of the conference, they want to start off their day with queuing theory. I'm assuming everyone had enough coffee to get through this. So this is going to be a talk on queuing theory and what it means for the systems we have to scale and keep running. I'm not going to go into a whole lot of details based on the timeline, but enough to build some understanding and intuition regarding what it tells us about system performance. So over the last 2 years, I decided to get an MBA. Hopefully this video doesn't get posted before I graduate. But I'm sitting in an operations class one day learning about queuing theory, and I start remembering other places I've heard some of these concepts, including past USENIX conferences. Next thing you know, I'm back at work and realizing that even some of the really smart performance people I work with don't fully understand the things I was learning in the class about performance. So the obligatory about me slide. My name is Jeff Poole. I've done several nerdy things in my career, including hardware design, software, and operations. I bike and ski. I collect certifications. And I like to propose talks I'm unqualified to give and attempt to be qualified to give them by the time I'm on stage. I'm looking for the panic expressions now to figure out who was part of the selection committee for SREcon. And I'm currently a director at Vivint Smart Home over 4 software teams and an operations team. So why the focus on queuing theory? Queuing theory is another tool in the toolbox for understanding the performance of systems. The math shows some nonlinear and surprising behavior, and I'll try to cover it, some of the math, but mostly to help build intuition for those who get intuition from looking at equations. If your eyes glaze over every time an equation comes up, that's fine. Really, I just enjoy typesetting equations. To tie back to some previous talks at this conference, queuing theory helps you build a mental model about your system's performance. It can also help you realize when you're approaching the performance boundary of the infamous fish diagram, I think it's called now. Okay, so what is queuing theory? This isn't going to be a full academic treatment, so I'm just going to go over the basics of what's needed to understand system performance. It's really all about the behavior of work getting done when work may have to wait, be queued, before getting processed. Most systems can be modeled as a series of queues and servers. So there are some obvious cases, like the movement of work through a factory, calls coming into a call center, and really anywhere that lines of people form. These are often covered in operations courses, which show up both in business and systems engineering curricula. In technology, there are some obvious areas where queuing is important. Many software systems include some kind of work or message queue, but it turns out many aspects of computing performance are dominated by queuing under the hood. Queuing happens anytime work can come into a system that isn't able to handle it immediately. It's how you manage transient mismatches between demand and capacity. So one example, if you look at the definition of the Linux load average, it shows the number of tasks currently executed by the CPU and tasks waiting in the queue, specifically the ready queue. One can imagine there's often more tasks that want to execute on a machine than there are physical processors or cores available to execute, so they must wait until they can run. Now you can't read it, but IOStat, if you've ever looked at that, it's full of queuing metrics. Turns out block devices are a common place where queuing happens. Reads and writes get queued up. You get statistics around utilization, queue size, and things like that. So the performance is often dominated by that queuing behavior. So we'll get into some of those details in a moment, but let's start with some of the concepts in queuing theory. Okay, first let's talk about parts of a system. In general, there are inputs, outputs, and some process is done to turn inputs into outputs. In the terminology of queuing theory, the piece that does the work is called a server. This is both convenient and confusing when talking about technical systems, since sometimes the server is in fact a hardware server. Sometimes it is a system that contains servers. Sometimes it is one process on a physical server. So it can get a little bit confusing in that regard. But in queuing theory, a server is just a part of the system that does work. And the earlier examples could be a cashier in a grocery store, check out a call center agent, or a CPU core, or a drive within a server. Because work usually doesn't come into the system in lockstep with the processing rate, there's typically some way of storing input that's ready to process. The simplest way to do this is with a first in, first out, or FIFO queue. Okay, I'm going to go through a few quick terms and parameters that I'll mention through the talk. Again, there's some nice Greek letters. Don't stress too much if you can't remember them. I'll try to use the real words when I can. So we have the arrival of tasks into the system, the arrival rate represented by lambda, and that's a common parameter. We also typically use a capital X for the rate of completions. In steady state, if you're looking at something for a long enough period of time that can keep up, you're going to have those be approximately equal. So usually we can just deal with one of them. And a quick side note, it turns out that operations textbooks and math books use totally different notation for all of this. So I'm on more the mathy side, but hopefully I don't confuse the two. So for the server itself, there are two parameters we care about. First is utilization, which is represented by the Greek letter rho, which is how much of the time the server's busy doing work. So 50% utilization means it's busy half the time and idle the other half. The other parameter is the mean service time, represented by the capital S, which is the average amount of time the server takes to do work. So it's the time it spends actually doing work. Finally, we have some parameters that are more associated with the queue. The waiting time, represented by capital W, is the average time work is expected to wait in the queue before getting to the server. The residence time, represented by capital R, is the average time work is expected to be in the system, which is the waiting time plus the service time. And finally, capital Q represents the average number of requests in residence, both in the queue and currently being processed by a server. Just because nothing on queuing theory is complete without mentioning Little's law, there's a few different formulations of it. It's a fairly simple set of relationships, and there are a few ways to look at it. These actually seem somewhat obvious, but it turns out that proving that these are that you can use averages in a system that's highly variable was not trivial. The real value here is if you happen to know two of the three values in any of these equations, you can find the remaining one. So the first version I've shown here is that the average queue length is the average arrival rate times the average residence time. For example, if you have a system that gets an average of 1,000 requests a second and takes an average of 10 milliseconds, 1/100th of a second to process a request all the way through, you know you will have 10 requests in the system on average. The second version is that utilization is equal to the average arrival rate times average service time. So if you know the utilization of a system is 50%, or 0.5, and the arrival rate's 10 per second, the average service time must be 0.05 seconds. Okay, so capacity and utilization. Let's talk a little bit about how queues work with some simulations. We're only going to talk about cases where the long-term incoming rate is such that long-term utilization is less than 100%. It turns out if you have more work coming into a system than you can possibly handle, it really doesn't matter how much theory you know, your system is broken. So utilization in our examples will always be less than 100%. So here's my little model of a queue. This is at 80% utilization, and this is with a constant arrival rate and constant service time. So every second a job comes in, and it takes 0.8 seconds to complete. You can see that there's no queuing because 0.8 seconds after a job shows up, the system's empty. 0.2 seconds later, a new job arrives and gets processed immediately. This is often what people think when they hear something's at like 80% utilization. They're like, oh, it's doing nothing 20% of the time, and the rest of the time it's just processing everything as it comes in. But that's not usually true. So what happens if we add some variability to the arrivals? Intuition tells us we may see some queuing because a task could show up less than 0.8 seconds after the previous task. So this model is also at 80% utilization, but the time between arrivals is determined with an exponential distribution with the same mean, but now it varies. I've sped up the animation for convenience because I don't think anyone wants to sit here and watch it for minutes. You can see that sometimes tasks appear and execute with no delay, and sometimes they appear too close together and start to cause queuing delay. Since the graphs were uninteresting in the previous version, I'll mention them now. The graph on the top left tracks three things. The large blue dots, which turns into a line over time, represent the mean waiting delay in terms of a multiple of the service time. So, in previous animation, it was always 0. A delay of 1 would imply we spend just as much time waiting as we do executing any task. So the average service time and the average wait time would be the same. I also have some small blue dots which show the short-term averages just so that you can see what's going on better. And then the large red dots are the 95th percentile wait times. When we look at the performance of our systems, average times can be misleading, especially when the worst latencies are dramatically longer than average. The 95th percentile shows us a level where 5% of our requests will have worse latency, so 1 in 20 tasks will take longer than the 95th percentile. You can see here the average wait is about 2 to 3 times the service time, and the 95th percentile ends up between 6 to 8 times the service time. So what happens if we actually kept the arrival time constant and changed the service time to be variable? Well, that's this case. You can see sometimes the service happens fast, sometimes slow. Once it speeds up, it's a little hard to tell. But they're all arriving at the same rate. And you can see we end up with very similar results. Occasionally, some longer service time will cause other requests to back up behind it. They'll eventually clear. But they can stay for a long time if too many long service times happen to occur in a row. And we also see the system occasionally just sits idle for a moment. So the real question is, what happens if we have both variable service time and arrival time? And that's this one. By the way, if anyone's needing to do a talk and looking for a good way to procrastinate, deciding you need to write your own animations to simulate stuff and demonstrate it, I highly recommend it. So here's a hint. This doesn't get better. Once you have variability in both, the parameters compound. So the server is still at 80% utilization, so it has free time. And if we looked closely, we'd see it is in fact idle 20% of the time. But having some idle time doesn't mean everything's fast. And if we think about it, this is a pretty normal state. Certainly we don't expect visitors to a website to coordinate when they go to that site. Even automated systems rarely behave. At Vivint, we have over 2 million homes that talk to our back end, and it's hard to do much better than having them follow policy of exponential backoff with jitter if they have trouble talking to the back end servers. Coordination at that scale is impractical. So we expect the arrival times to be randomly distributed. Service time is a little less clear. If you imagine a web service that does nothing but perform a mathematical operation on a lightly loaded server, it's possible you can have relatively stable service time. But if a service has to use a disk, talk to a database, or call additional services, it's likely to have a wide distribution of service times. And very few of us can convince our companies to invest in extra compute just to make sure that our servers are mostly idle. So the key here is that variability in either arrival time or in service time can cause queuing in a system that has enough capacity for the work. And most systems have variability in both. Trigger warning for equations. So for a single server, single resource, the time in the queue is a multiple of the service time by the utilization over 1 minus utilization, which is the idle time, multiplied by this nasty thing on the right side. So CV is the coefficient of variation. It's a statistical measure of how variable the arrival and service rates are. And the nice thing for us, let's see, so basically these terms break into how busy a system is and how variable it is. So the nice thing for us, when everything comes in at a constant rate, those coefficients of variation turn to 0, and the wait time becomes 0, which is exactly what we saw when everything was constant. Turns out with exponential distributions, which is what I've conveniently used for all of these, it actually, the coefficient of variation is 1. That's the standard deviation divided by the mean. So the nice thing is that 1 squared plus 1 squared over 2 turns into 1, which means that term just disappears. So keep in mind, extremely variable inter-arrival or service times could make the right term much larger than 1. And if one of the terms is 1 while the other is 0, so for example, the examples I had were we had a constant arrival time and a variable service time or vice versa, then it ends up being about a half. One thing to note about these assumptions is the models I'm using are memoryless, so they assume that the arrival of one task isn't related to the arrival of any other tasks. On a large scale, that often can be seen to be true, but you can imagine that, for example, if you're looking at a network system and you receive a packet, it is likely you'll receive further packets. Things tend to happen in bursts in a lot of real-world systems, and that sometimes can affect the math. Okay, so we played with variability. The next question is, how does utilization affect latency? So far, all my examples have used 80% utilization to give us a nice level that's high enough but has some room. And the answer here is that it affects latency more than most people think. I've heard comments where people said, hey, this can't be slow because of CPU, because the server's still got 20% idle time. Well, some of the time, really what it is some of the time it's not doing anything, some of the time it's backed up. And this is the basic model for a single server process. And the y-axis here I've got as multiples of the service time. So no point putting actual units up here. So that shaded area at the bottom is the service time. You can see at 0 utilization, you expect that the time task will stay in the process is the service time. Obviously, as it goes up, you get more queuing. So at 50% utilization, you actually expect a mean residence time of 2 times the service time. So if you've got a process that, it can respond to requests in 1 millisecond, and you're at 50% utilization, it might be 2 milliseconds that you're seeing on average. If you go up to 75% utilization, it's now 4 times the service time. So a 1 millisecond request might be seen by the outside world as taking 4 milliseconds. And this is actually a consistent pattern that makes a good guideline. Every time your idle time gets cut in half, the expected residence time doubles. Again, this is for pure mathematical queuing systems, but these end up being pretty good rules of thumb for real systems out in the world. So we saw in that case where when we went from 50% to 75% utilization, our idle time cut in half from 50 to 25%, and the expected residence time doubled. Just to continue the pattern, at 90% utilization, that multiples 10 times the service time. So a request that takes 1 millisecond to execute would have an average latency of 10 milliseconds when the waiting time is considered. So I think it's worth considering if you've ever had multiple copies of a service running on servers with dramatically different load. And think about what it might mean if the average response time of the service on one server might be 2 or 4 or 10 times the average response time of the same service running on a different server, just because of the neighbors that they have, the other work running on that machine. And the situation gets worse if you want to look beyond the mean. So to paraphrase a former coworker of mine, when you get a few million messages a minute, 1 in a million events happen all the time. Anyone operating at that kind of scale is going to see 95th percentile events happening all the time. You're going to see 99th percent events happening all the time. So these are the curves for expected residence time for the mean 80th, 90th, and 95th percentile. If anyone wants the little rule of thumb numbers, it's there. These slides will be up, so you don't have to furiously write down numbers if you care about this for some reason. And then just to show when we look at this, the 95th percentile, at 50% utilization, we're already up to 6 times the service time. 75% utilization, 12 times the service time. And 90% utilization, I had to rescale the graph to get 30 times the service time on there. So you can see that when systems get heavily loaded, their performance is non-linear in terms of how it degrades. If we look at our earlier data for 80% utilization and the variable arrival and service times, the chart on the top predicts an average wait time of 4 times the service time and a 95th percentile of 14 times the service time. The graph we actually got was about 4 and about 13, so the simulation does match the prediction. Another useful table, if for some reason you want to look at it, like I said, the slides will be online, so if you care about these things, I would grab it that way. But you can see up at the 95th percentile at 90% utilization, you're at 30 times the service time. Okay. So another question that comes up is we often don't just have one server. We have lots of things that do work. So should you have a queue per server or one queue feeding all the servers? We don't actually have to run a new simulation to see the 2 servers with their own queue, because it's exactly the same as one server with its own queue. There's just 2 of them. So it does twice the work and has exactly the same performance characteristics. But might as well add a feature to my simulation. Now we have 2 servers pulling off the same queue. I did have this double the incoming rate, because I need to keep the utilization of these servers the same as the previous example we were using. So the utilization of each of these servers is 80%, but we're pushing work in twice as fast. And this does use the variable arrival and service times, because that's the most interesting part. So it turns out this is much better than what we saw for an individual server with an individual queue. The average wait is actually close to 1 time the service time versus about 4 for the single queue. And the 95th percentile only gets to around 4 times the service time. Another trigger warning. So this is an approximate formula for multiple servers. I say approximate because the real server, or the real formula, uses Erlang's C function, which if anyone's seen it is horrific. 3 factorials and a summation in it, so I don't want to take up the whole slide, and this is very close, so it works out. But you can see it's a very similar form to the previous one. In fact, if we compare it to the one server version, the variability part's the same. Really what we have is the 2 differences. So in the how busy part, we have an exponent on the utilization. And if you plug in 1 for the number of servers, that exponent goes to 1, so these end up being the same. And then we also divide the service time by the number of servers, which sort of makes sense if you think about it, because the waiting time is going to be based on some multiple of the service time. Well, if you've got 10 servers, you're probably waiting for 1/10 of that time for the same work to go through it. And this causes the residence time to grow at a different rate. So this is graphing just a change in number of servers. It's the same graph we had before for the mean residence time, but this time the number of servers is changing. What you see is that when the number of servers increases, pulling from the same queue, the bend gets sharper. So you start degrading later. And you can sort of get this intuition. Imagine you're in a grocery store and there's a bunch of checkout lines open, and you just get into one at random. Well, it's possible you're standing in a checkout line while there's a cashier down the way that's doing nothing, just waiting for someone to show up. On the other hand, if you've ever been to a store that has a single queue, I think Best Buy does that these days, there's a few other places, you don't have that problem. Occasionally you're the one standing at the front of the line and they're like, excuse me, hey, I'm open over here. But the idea is whenever there's a server available, the next person gets access to it. There is a caveat in the real world though, which is that you can't always centralize your queues for a couple of reasons. But imagine you've got some sort of queue and a bunch of servers across a network. Well, when a server finishes its work, if it then has to reach out across the network to get work, you are now adding latency where nothing is getting done, and that's going to break it. So one way this is often solved is with prefetching. And if you prefetch, you're basically putting a small little queue on each server. So it's rare to see a case in a distributed system where you have one queue and a bunch of servers pulling work from it. Okay, so let's talk about a little bit of practical stuff for those who care about these things. The important disclaimer, just about everything practical is an approximation. It turns out that nothing is perfectly modeled just about ever, but certainly we're looking at rough estimations about how a system will work. So I don't know if anyone here has experience with USENIX. I'm believe there's a few similar tools for other languages, but we've got some legacy code that's Python that runs under a server called USENIX. And what USENIX does, it spawns a bunch of Python processes and hands web requests to them. Each USENIX process has its own request queue in case a request comes in that it doesn't have an available process to service. So the question here is, how many instances of USENIX do you run versus how many Python instances do you run behind them? So say you need 500 Python processes to handle your system's load. Should you run one USENIX instance with 500 Python processes behind it? Or should you run 5 instances of 100 processes each, 50 instances with 10 processes? So we know from our earlier work that one queue feeding a lot of servers is going to have lower expected latency than a lot of servers with their own queues. This would lean us towards the side of one USENIX process and 500 Python processes. But that's not the only factor to consider. It's the unfortunate problem with the real world is the answer is always it depends. If you run one copy of USENIX and it fails or gets slow, you are down. So you've got a blast radius of your entire system. That's probably not what you want. So you probably want more than one. Now if you run, say, 2 of them with 250 processes each, if you want to do any scaling, your options are now to scale up or down 250 processes at a time. So there's also a little bit of granularity there that you might want to gain by having a smaller processes, even if you lose a little bit of latency. In the end, like I said, it depends. These are trade-offs, but the idea is that you at least need to understand that theoretically the lowest latency option is putting everything behind one queue so that you at least know what that end of the trade-off is. Look at these graphs again. If you think about CPU usage, often you'll see processes following a similar performance curve. The idea is that if your CPU is at 90% utilization, that doesn't mean you've got room for 10% more work. It only has room for 10% more work if you do not care when that work completes. This is really the difference between real-time systems and batch systems. A batch system can run at 100% utilization, but you may give it a pile of work, and some of that work may come out 4 hours later. So that's not how you want to run an interactive website. So as a guideline, I generally try to keep anything below 80% CPU usage because that feels like the part of the curve where things get nasty. Again, there's not a hard discontinuity here, but if you're looking for a number to point at, 80% is a good number. If you are very latency sensitive, I would stay below 50%. Again, very few of us will be able to convince our companies to buy a bunch of servers so we can run them at 10% utilization. So there has to be some pragmatism here, but at 50%, you are doing pretty well in the latency perspective. Now I'll give you something from our data set. So I pulled a few graphs of real data, trying to find some good examples. This is one of our MongoDB servers. And I plotted the CPU core utilization on the y-axis and the queries per second on the x-axis. So for the most part, this is nice and linear. You can see that we get more queries, we use more CPU. But it always makes me feel a little bit funny if near the top end of the graph you see things start spreading upwards. That tells me that sometimes under high load we use a lot more CPU than this would predict. Now let's look at a slightly different metric. So here, latency per query is on the y-axis and core utilizations across the x. The latency is normalized, so what I did is I got the smallest data point I had for latency and considered that the service time and divided everything by that. So 1 on this is the lowest latency queries we have. Couple things to notice here. So one thing I'll say, this is all just using normal Prometheus data from the MongoDB exporter. So I found that in a lot of talks about this, it's not always clear where people are getting their data from, or that they have to run some complicated testing harness to get it. This is literally what MongoDB is reporting to us. So it probably misses some stuff. Good examples if there's potential latency sources outside the server process itself. It doesn't show if there are connections in the connection queue waiting to be accepted. It doesn't show if there are queries stuck in the TCP buffers. And fun fact, does anyone here use RabbitMQ? Let's see if you, okay. If you've ever seen it slow down and you can't figure out what's going on with it, it's nice to look at the TCP buffers. We run a decent amount of RabbitMQ, and we have an alert that tells us if there's more than 200 megabytes of data in the incoming receive queue. Turns out that Rabbit, when it gets stressed, is really bad at reading packets. And so you'll be like, oh, there's nothing in the queue, but it's just going slow, and you realize that there's 200 megabytes, or I think the highest I've seen is, I think we got to almost 2 gigabytes of packets in TCP receive queues. Turns out that then your statistics about how fast your Rabbit queue is going are not real accurate, because there's stuff sitting in the ether between your code and the RabbitMQ server. So anyway, with this graph, a few things to notice. One is I'm not real excited about how it just sort of spreads as you get to the high CPU utilization end of things. And then if you look at the bottom of that graph, the way it curves up, you don't get any fast queries above 50% CPU usage. The fastest queries are still notably slower than anything you see at low CPU usage. So if I put some familiar curves on here, you might start seeing something that looks more familiar. So these are the expected residence time curves. The green one is the graph for one server. It's too pessimistic. This is a multi-core machine. That's not what we get. The red line is actually for 72 servers, and I picked that because this is a 72-core machine. It's hyper-threaded. We don't actually get to use all the 72 cores. And then MongoDB is not actually running an independent process pegged to each CPU core that are all independently responding to queries. So we don't get the full power of 72 cores on this. But I did just run a little fit, and 6 to 7 servers is about what fits the data. So there's a few things when I see this. One of them is that, well, I don't like the fact that 80% utilization is even getting on this graph, because that's not a good sign. It also tells me that we're probably entering an area of performance where our latency is going up dramatically, especially where this is just what is seen within MongoDB, not what clients are seeing across the network. This also tells me that a certain coworker in this room who suggested we would need to add some database servers to our cluster before our annual peak this fall probably was correct. And we probably should look at doing that before our load goes up much. Just for fun, these are the Prometheus queries I used. So like I said, literally they're just using stuff from the MongoDB exporter, which pulls from the server status, MongoDB server status, and it's operations latencies, and then the count of operations, and then it's got, I did a little bit of jumping through hoops for CPU utilization to turn that into a not idle percentage. But here if anyone wants to try to do similar things. Unfortunately, Prometheus really likes to graph time series, so it doesn't really let you do these sort of one parameter against another parameter types of things. So if anyone is really excited to do this, I can show you some code that I have that pulls it into Python. So some other things you can do if you want to use queuing theory and look at performance. One of them is you can actually build a few queuing model of your system. So Neil Gunther, you'll see his name show up a few more times here. He's a little bit of the godfather of all this stuff. So he's got a tool called PDQ, and you can give it a whole model of different queues and servers, feeding different queues and servers, and then you can have it predict performance about them. You know, the quote, all models are wrong, but some are useful, comes up here. You're never going to exactly model your system, even to the point of, you know, there's queuing in the network, there's queuing for the processor, there's queuing for everything. And so it's queues upon queues upon queues, and it would be unwieldy if you put everything possible in there. But you can build a reasonable model. So this is sort of the bottoms-up approach, where you know what the components of a system are, and you're trying to build a model for it and get some information about it. And I've got links to all this stuff in the slides that'll go up later. And really, you need some experience to know what details are important, is the challenge here. Neil again. So he's also known for coming up with the universal scaling law. Equations at the bottom. I decided not to do a big tutorial on this. There's actually some good talks on that, especially in past USENIX history. But this basically says that, okay, in a perfect world, things scale linearly. But most things don't actually scale linearly. So this takes two components. There's this sort of started with Amdahl's law, for those who are familiar. Basically says you can only speed up something by parallelizing it, by looking at how much of it's parallelizable. So if 5% of something's serial and 95% is parallelizable, you will never get faster than 5% of the original time, because that is always serial. And then it adds another component which says that a bunch of real world systems, there's a lot of coordination that has to happen in them. And if you scale up too much, that coordination goes up with the square of things in the system. And so that can actually make your performance curve back down the other direction and get worse as you scale it up. Typically you get a bunch of data and you fit it to this equation, and it hopefully predicts areas you don't have data for. But it is a lot easier than having to go through your system and figure out what series of queuing systems need to be tied together to exactly mimic your production system. So just some of my little guidelines on one slide. You know, really, every time your idle time gets cut in half, expected your residence time to double. So effectively, your latency is going to double every time your idle time gets cut in half. I like staying below 80% CPU usage, or 80% utilization of just about anything. Lower if you're latency sensitive, and 50% is good if you are especially latency sensitive. And then increasing variability makes that utilization latency graph get worse. Doing more servers off of one queue makes it get better. So those are things to consider, and just some resources at the end. I've got 2 books by Neil Gunther, which are both sitting in my room upstairs. I decided not to bring them for visual aids. The top one's focuses on PDQ and it's about building the queuing systems. The bottom one tends to focus a little more on the universal scalability law. He's got a website too. He's got some talks out there. And then I threw 2 talks on here. It might be showing my age, because I'm pretty sure I saw both of these in person 7 years ago at a conference that either doesn't exist or has been absorbed into this one, depending on how you look at it. But Eben Freeman's talk on the queuing theory is fantastic, and I like just about everything Baron Schwartz does, and he mentions the universal scalability law. So that is it. Thank you.